In grade 9, you will remember that you learned about real numbers. Please take time and go to page 1 of your Mind Action Series textbook and just remind yourself about these things. You will find there on page 1 a summary of what rational numbers are and what irrational numbers are. For today's lesson, I want us to focus on the rational numbers. So remember, by definition, a rational number is any number that can be written in fraction form. Any number that can be written in the form A over B. And if you go to page 2, you will remember that rational numbers include all the whole numbers and all the integers. But first of all, just make sure that you remind yourself about what whole numbers are and what integers are. So whole numbers and integers are rational. Proper fractions are all rational. Improper fractions and mixed numbers are rational. Terminating decimals are also rational. And recurring decimals are rational. In this lesson, I just want us to look at the recurring decimals. In particular, we want to prove that every recurring decimal is indeed a rational number. Every recurring decimal can be written as a fraction in the form A over B. Remember here that A should be an integer and that B must also be an integer. And B cannot be equal to 0, otherwise we have a problem there. So let's look at just a few examples. Every recurring decimal is a rational number. And that is what I want us to prove. I think the best thing is let's pick an example. Let's show, for instance, that 0,3 recurring, we'll put that dot there to show that it's recurring. Show that that number is rational. Remember, rational numbers are represented by the letter Q. So how do you prove that? I'll show you one method of doing it. In other words, we want to show that 0,3 recurring can be written as a fraction. And so if we can write 0.3 recurring as a fraction, then that means we have proved that that number there is a rational number. So let that fraction be x. So we say let x be equal to 0,3 recurring. Now what that means is 3 keeps on repeating. So that is my first argument there. The technique is you can multiply by specific multiples of 10, not multiples of 10, but powers of 10. For instance, if I multiply this by 10, if I multiply the left-hand side by 10, and I multiply the right-hand side by 10, then the left-hand side will become 10x, and the right-hand side will become 3,3333, and so on. So that is my second equation. The intention here is for me to get, after the comma, to get the same digits or the same digits after the comma so that I can subtract. Now, right now, I can take equation 2 and subtract equation 1. And that will give me 10x minus x, which is 9x. On the right-hand side, 3.33 and so on, subtract 0.33 will give us 3. So now 9x is equal to 3, which means x is equal to 3 over 9. That is our answer. You can write that as 1 over 3. And so we have now managed to write that recurring decimal in fraction form, which proves that 0.3 recurring is indeed a rational number. I'll do one more example with you. Show that 0.34, I want 3 and 4 to be recurring. Show that this is a rational number. In other words, we can write this number as a fraction. I know there is a short way of getting the answers. Some of you can look at this and just tell me the answer straight away. But if you do get a question like this in an exam or in a test, remember that we want to see your steps. Just show us using your steps. Don't use a calculator. Just show the steps, and these are the steps that I'm showing you right now. So the process that I want us to use is this. Let x be that number there. Now that means x is equal to 3 and 4 are recurring, so that's 3, 4, 3, 4, 3, 4, 3, 4, and so on. I'll call that one my first equation. Right, I need to get more similar equations by multiplying by powers of 10. You can multiply straight away by 100 if you see and you know what you are doing. Otherwise, you can keep going in tens. Like multiply by 10, the left-hand side becomes 10x. Then the right-hand side becomes 3,43434343, and so on. Now, what I don't like about number 1 and number 2 right now is that after the comma, the digits are not the same. I want these digits to be the same, so I wouldn't use a combination of these two. So let me go on and multiply again by 10, and that will give me 100x. If I multiply by 10 again, then this becomes 34,343434, and so on. Now, if you compare number 3 with number 1, you will notice after the comma, they have the same digits, and those can easily cancel out or subtract and give us a 0. So I'm okay with 3 and 1. So I'll take number 3 and subtract number 1. That means 100x subtract 10x, that should be 90x. And then, okay, sorry, mistake. I want 100x subtract x, and that gives us 99x. And then 34,343434 subtract 0,343434, that will give us 34. And so our fraction is 34 over 99. Now you can take your calculator and check. Put this in your calculator. See whether that gives you 0.34 recurring. I'm sure that will do. All right. I hope that is clear. Maybe just one more example because I have time. Let's show this time that 0.312, but I just want the 2 to recur. Show that there is a rational number. Same method. Let x equals 0.312 recurring. That means 0.31, then the 2 is recurring. So it's 2, 2, 2, 2, and so on and so on. I'll call that one my first one. If you know what you need to multiply by next, you don't have to go step by step like I'm going to do here. I'll just do that because I think it's not quite a lot. So I'll multiply by 10. If I multiply by 10, the left-hand side becomes 10x. The right-hand side becomes 3,12222, and so on. Now, number 1 and number 2 are not going to help me because the digits are not the same. So I'll carry on, multiply by another 10, which gives me 100x. If I do that, then this becomes 31,2222, and so on. Once again, there's no combination here that is giving me the same numbers after the comma. So I'll go one more time, multiply by 10. So I get 1,000x, and this is 312,2222. There is my number 4. Now, number 4 and number 3 are interesting because they give me 2's after the comma. So I'll take number 4 and number 3. So take number 4 and subtract number 3. What do we get? 100x minus, sorry, 1000x, subtract 100x should be 900x. Then 312, remember those twos after the comma will give you 0. So it's really 312 subtract 31, and that should give us 281. Okay, please check that. That is 281. Then that means x is equal to 281 divided by 900. All right, there we are. So that recurring decimal there can actually be written as a fraction. So this is one method of proving that recurring decimals are rational. Please remember, every recurring decimal is a rational number.